So in the previous class we have discussed the AC circuits, behavior of AC circuit with a pure resistor, pure inductor, and in this class we will study the behavior of pure capacitive circuit. So purely capacitive circuit we are taking, and the circuit is like this. Okay, and this is our source. This pure capacitor of capacitance C farad. DC source is represented by pure sinusoidal waveform. So this is AC source. Then I have the voltage is plus minus VB, and current to the capacitor that is notated as I, small I. So we have to find out the relation between the phasor relation and other characteristics between the V and I. So yes, so you have consider this circuit in which the sinusoidal AC voltage source having the waveform function like this. V is equal to small letter v, that's equal to Vm sin omega t. Vm sin omega t. So this is our AC supply, and it is connected across a capacitance C farad. Okay, and we have already studied in our previous classes. We have the current I. Have the current I through the capacitor of capacitance C. We have the formula I is equal to C dV by dt. So Vc of t, Ic is equal to C into dVc of t. So Ic here it is I. So I will be equal to C into d by dt of Vc of t, means voltage across the capacitor. So that is nothing but V. So we will get C dV by Cv of t by dt. Okay, this is our equation. Now I am substituting for V of t, that is nothing but Vm sin omega t. So we will get C into d by dt of Vm sin omega t. So that is equal to Cvm cos omega t into omega. So that will be equal to omega c. Vm cos omega t can be written as sin omega t plus pi by 2. Okay, on comparing the equation 1 and this equation, we can observe that sin omega t plus pi by 2, the case of I. So that means I can be written as B can be written as Vm phasor at an angle 0 degree, and that's also is equal to V at an angle 0 degree, where V is our RMS value. Okay, similarly, we have the I. It can be written as Im at an angle pi by 2, that is 90 degree, that is plus 90 degree, and that can be also equate to IRMS. IRMS, I at an angle 90 degree, where I is our RMS value. So this is equal to V phasor, and this is, I'm taking it as I phasor. So you draw the phasor diagram. If you consider, then I'm taking V as my reference. Reference means coinciding with the x-axis. So this is my V phasor. I phasor will be plus 90 degree, 90 degree leading. So this will be like this. This will be I phasor. So 90 degree leading. So that means just that you can conclude that a pure is the pure in a pure a capacitive circuit, the current through the capacitor always leads the voltage across the capacitor, voltage phasor. So we have the two phases which can be mathematically modeled as V is equal to V of t is equal to Vm sin omega t, and I of t, or I, simply I, is equal to Im sin omega t plus pi by 2. Now I'm substituting for omega t. I have omega t. I'm taking it along the x-axis, and V, okay, and I values, okay, V and I values like this. So V and I values on y-axis. So omega t, that means equal to theta. So if you substitute theta equal to 0, then you will get b equal to 0. And but I is sine pi by 2. So sine pi by 2 is 1. So you will get Im. Now theta, for theta is equal to pi by 2, we substitute b will be equal to Vm, and this I will be equal to 0. So like that, theta equal to pi, if you substitute, then b will be 0 and I will be equal to pi plus pi by 2 and 3 pi by 2. So sine ind and will be minus Im, and like that, if you substitute 3 pi by 2, you will get this is minus Vm and this is 0. So like that, if substitute, if you will get for every value of theta, you will get V and I, and if you plot the waveforms V and I, you will get exactly like this. Okay, so this is V comma I, and this is our V waveform, this is our I wave. That is, for theta equal to 0, okay, you will get I is equal to Im and V equal to 0. And theta equal to pi by 2, you will get V is equal to, yes, pi by 2, V is equal to Vm and I is equal to 0. That means this point, that is I equal to 0, V is equal to So like that you will get all the points, and if you draw a smooth line joining all these points, then you will get this waveform. Okay, that means two sinusoidal waveforms in which the current waveforms lead the voltage waveform by 90 degree. That means leading means if you extend this x-axis to minus x-axis, okay, this is minus x-axis, then what you can observe is this current waveform, that is I, is actually started from minus pi by 2, theta equal to minus pi by 2. Okay, that means pi by 2 radian earlier. So that means this earlier means leading. Okay, so you can conclude that in pure capacitive circuit, the applied voltage, and the current through the capacitor leads the voltage by pi by 2 radian or 90 degree. Okay, so we have taken the voltage phasor as our reference. So we have V, voltage phasor V, that is V phasor. Okay, V phasor like this is equal to V at an angle 0 degree, where V is our capital V is our RMS value of the voltage, and this is in polar form, and I can convert this polar form into rectangular form. That means R into cos theta plus J sin theta. That means V into cos 0 plus J sin 0. That means equal to V plus J 0. So this is V plus J 0 volt. Now the current phasor I will be equal to I at an angle pi by 2 or 90 degree plus 90 degree, and when it is converted to again in rectangular form, then you will get I into cos 90 plus J sin 90. So that will be equal to 0 plus J I, where I is our RMS value. Where V and I are RMS values. And are given by the equation respectively is Bm by root 2 and Im by root. Okay, so now we have from the maximum value of current Im of the circuit from equation you can from this equation 2, from the equation 2 I have let me show that equation. Or from equation number 2 I have I equal to omega c Vm sin omega t plus pi by 2. So we have the general format, that is I is equal to Im sin omega t plus pi by 2. So that means you have Im is equal to omega c Vm. Okay, and Vm by Im, and that's equal to also V by I, you can say. That means if you divide by root 2, then you will get the corresponding RMS values, that is V by I, and that will be equal to 1 by omega c. Okay, so our problem our we will get a new terminology or a new quantity, that is V by I. Okay, by Ohm's law, this is nothing but some analogous quantity of resistance. Okay, and in pure capacitive circuit, or in the case of a capacitor, this V by I is known as is equal to XC, that's equal to 1 by omega C, and it is known as the capacitive reactance, and it is notated as Xc. So the Xc magnitude is 1 by omega C, where that is equal to 1 by 2 pi Fc, where this omega can be written as 2 pi F. Okay. Again, the unit of this capacitive reactance is equal to, again, ohm. Why? Because we have V by I. In general, it is resistance, and its unit of resistance is ohm. And when the circuit is pure capacitive, okay, capacitive or inductive, pure inductor, then we will call it as reactance X. So if it is pure inductor, then XL, that is inductive reactance. Then if it is pure capacitor or capacitance, then it is notated as Xc, that is capacitive reactance. Again, the unit is same, ohm and ohm. Okay, now we can define the Ohm's law also here also. That means we have V by I equal to Xc in a pure capacitive circuit. Then we can write it as V by Xc equal to I. Okay, IC you can write, that is capacitive current, the RMS value of current passing through this pure capacitor. Okay, so if you have this, if you know the RMS value of voltage and RMS and Xc capacitive reactance value is also given, then you can find out the RMS value of the current through the capacitor. Okay, so and also any two of these is given, then you can find out the third one, okay, by this formula. Now we have to discuss the power and power factor. Power and power factor. The concepts are similar to what we have discussed in the previous classes. That means we have the instantaneous power formula P. Small p is equal to the instantaneous value of current multiplied by the instantaneous value of voltage multiplied by instantaneous value of current. Okay, so and its unit will be watt. Now we have the two waveforms, V and I waveforms, and so that we will multiply point by point and we will get the power waveform like this, okay, as shown in the dotted line. So that means positive into positive, you will get positive up to 90 degree, and negative into negative again, positive, that is plus V and I is negative in the interval 90 to 180 degree. So positive into negative, you will get negative. So this half you will get, and this the entire yes concept is repeated after 180 degree. So the power waveform is also known. Now you can say that this is symmetrical about the x-axis. So if you find out the area over the entire cycle, that is 180 degree, then you will get positive area and minus negative area. So both are equal. So if you compute the average value of power, then you will get 0. So active power or average power or real power is 0 in the case of a pure capacitive circuit. Okay, so that means yes, that means the average value of power is 0, means the whatever the source, whatever power is supplied by the source to the load, whatever power it supplies, that power is absorbed in the next, or is returned in the next half cycle. That means from 0 to 90 degree power is positive. That means the power is positive, means power flows from source to load in like this, as indicated in this direction in this figure. Now the from 90 degree to 180 degree, that means the next half cycle, during the next half cycle the power is negative. That means the direction of power flow is exactly reversed. That means from load, that is from capacitor to source, the power is flowing. That means the net effect is 0. That is what you mean by average value of power, and that is equal to 0. Okay, so now yes, so we will get, yes, we confirm that the real power in a purely capacitive circuit is given, okay, is proved to be 0, and it is given as P, capital P, that's equal to, we have the formula V into I into cos theta, where V and I are the RMS values and cos theta is the power factor. Okay, so that is equal to 0 means actually V is not equal to 0, and V is via RMS value, that is not equal to 0, that is Vm by root 2, and I RMS, that is also not equal to 0, because that is again Im by root 2. That means cos theta, our power factor, is equal to 0. So cos theta equal to 0. So theta, where theta is the angle, phase angle, okay, between V and I, V phasor and I phasor. So that is, we have seen that it is 90 degree. So theta is equal to 90 degree. So cos 90 equal to 0. So the power factor PF in a pure capacitive circuit, AC circuit, will be 0. Power factor will be 0. So we call it as 0 power factor, ZPF. Okay, actually in the pure inductive circuit also we got 0 power factor. Okay, but in order to differentiate these two 0 power factor, The first one is known as the zero power factor lead. The second one is zero power factor lag. That means zero power factor lead means here the current leads, the current phasor leads the voltage phasor by an angle 90 degree. And in lag, the current phasor lags the voltage phasor by 90 degree. So the power factor definition, if you recall, it is nothing but the factor by which the factor to which the it is to be multiplied to the apparent power, so that you will get the average power or active power. So that means that factor is 0 means your active power or average power is 0. That means you have to multiply the apparent power, which is Vi, by the factor 0, so that you will get the active power or real power, that is real power or average power, that is equal to 0. Okay, so that means the whatever it is given by the source, it is in the very next half cycle it is taken by the source itself. So that means, as I explained in the previous classes, that means you have I am the source and you are the load. Let us imagine like that. Then as source point of view, I have given 10 mangoes to you. That means you means load. Okay, and that 10 mango is my apparent power. Okay, and in the next, after some time, I have taken all the 10 mangoes back to me. Okay, that means yes, the net number of mangoes that is in your hand is 0. That means the real number of mangoes is 0, effectively 0. That the same logic can also be applied here. So so far we have discussed the R alone, L alone and C alone AC circuits and its behavior, that is phasor relationship. So we will summarize the entire discussions. Okay, so we will have a tabular column like this, that is property, then resistance, inductance and capacitance. That means resistance alone, inductance alone, capacitance alone, or capacitor. That means resistor alone is kept or is connected to the AC source, then inductor alone is connected to our AC source, then capacitor alone connected to our AC source. So what the property we are taken is current. Okay, current, then frequency dependency, then power, then phase difference and reactance. Okay, reactance in resistance it is R. So one by one we will take, that is current. In the first case it is V by R as our Ohm's law, where V is our RMS value. Okay, then in inductive circuit, pure inductive circuit, that is V by XL, and in pure capacitive circuit, that is V by XC. Then frequency, that means whether this this resistance is having the frequency term or not. That is what you mean by frequency dependency. So in R you don't have any frequency term because R is equal to rho L by A. But in the case of XL, that is inductive reactance, that is XL is equal to omega L, and that's equal to 2 pi FL. So XL you can say is equal to a constant K into F, you can say. So this is nothing but proportionality constant. So you can say that XL is proportional to F. Okay. So frequency dependent. Then again Xc, similarly you will get Xc is proportional to 1 by F, reciprocal. Okay, so inverse relation will be there. Now power, we have V into I, and that's equal to I square R or V square by R. These are the formulas. Now active, here the power means this is nothing but active power, not the apparent power. Active power or average power or real power. So in the case of pure inductive and capacitive circuit, these are 0. Now phase difference, in pure resistive circuit it is in phase, that is 0 degree, and in pure inductive circuit it is 90 degree, and in the case of pure capacitive circuit, actually this is like this. Okay, and for pure capacitive circuit it is again 90 degree leading, and this is lagging, 90 degree lagging. So V, this is I, and this is I. Okay, so then reactance in pure resistive circuit it is known as resistance, and pure inductive circuit it is inductive reactance, that is XL, JXL, and that's equal to J omega L, that's equal to J 2 pi FL. And in the case of capacitive circuit, pure capacitive circuit, it is 1 by omega C, that is 1 by 2 pi FC. Okay, so that's about our comparison also. Okay, now we will move on to the next topic, that is series RL circuit. Series RL circuit. RL circuit. So suppose I have a resistor like this of resistance R ohm, and I have a inductor, pure inductor of inductance L Henry, and I have connected this in series like this. That means the finishing end of the resistor is connected to the starting end of inductor. Okay, and I have this is as a whole, I'm taking it, I'm considering it as a load. So this is our RL series load, or network, you can say network. So this is RL series network. Actually, in order to make this as an RL series circuit, you have to close the circuit, you have to form a closed path. So the closed path is formed by connecting it to the AC source like this. Now this became a series RL circuit. Okay, circuit. And I have this V, that's equal to again Vm sin omega t. I will no more write this again, and I will represent it as a phasor like this, V phasor. Okay, and I have the current flowing through this circuit. Since this is a circuit, a closed path, a current I will flow. Okay, and this this is again a phasor, and it is denoted by I phasor. Okay, now yes, we have I'm representing the voltage drops. Voltage drops. That means by Ohm's law we have V is equal to IR. Okay, we have the for the pure inductor we have the reactance, inductive reactance XL in ohm, and for pure resistance we have R ohm. So when a current I is flowing through this RL series circuit, voltage drops are caused or developed, and that voltage drop is having the polarity plus here and minus here, and again across the pure inductor it will be like this, plus and minus. Okay, now I am representing the voltage drop across the resistor, it is VR, and across pure inductor is VL respectively. And this VR and VL is no more a VR and VL are actually instantaneous representations. So we have this VR phasor and VL phasor. Okay, so now I am applying the KVL. Applying KVL. Okay, if you have to apply the KVL, then we have in general we have if plus minus V, small letter V, which is the instantaneous supply voltage, and VR is our instantaneous value of voltage drop across the resistor, and VL is the instantaneous value of voltage drop across the pure inductor. Then according to the Kirchhoff's voltage law, I have this plus V, then plus to minus, it is fall in potential, so minus VR, again plus to minus, again fall in potential, so minus VL is equal to 0. So these are, so for this RL series circuit, applying KVL, you have to consider the voltage drops as instantaneous values only. Okay, so you can write this V as your V phasor, and VR you can replace this by phasor corresponding phases. Okay, so suppose we have V phasor is equal to RMS value is 10 and VR is RMS value is 5, then VL its RMS value is 5 again. Okay, then you cannot write it as 10 is equal to 5 plus 5. You cannot write this. Why? Because this is not the simple arithmetic addition but phasor addition. Okay, you have to add or subtract phasor by phasor. Okay, vector addition and vector subtraction. So this is not simply our arithmetic operations. So you have to keep that in mind always. Okay, so now I am going to we are going to study how to draw the phasor, how to draw the phasor diagram for this RL series circuit and for any AC circuit. How to draw a phasor diagram. So here we have to apply our knowledge about the phasor relationship between V and I, voltage and current, in pure resistive, pure inductive, as well as in pure capacitive loads. Okay, that topic or that concept you have to remember, or you have to keep that in mind in order to draw the phasor diagram for RL series circuit, series circuit, or RC series circuit, or RLC series circuit. Okay, that means any combination of these R, L, and C. Okay, so there are 6 steps involved in drawing a phasor diagram for any AC circuit. So that will, if you have to study in this video, it will be very lengthy video, so that we will discuss that in the next video lecture. So thank you.